Welcome everyone to theme 2 in part 2, Learning for Autonomy. Just a few quick announcements for the other speakers who are presenting after me. This session is being recorded, so when you talk, please talk into the mic. Okay, so for those of you who don't know me, my name is Yisong. I'm a professor of machine learning here at Caltech. I've been at Caltech for 9 years now. And today I want to talk to you about some of the work and research directions that my group and collaborators have been working on in neurosymbolic programming. So there have been many exciting success stories in machine learning, such as beating the world champion at Go, cooperative multiplayer games like Dota, AlphaFold, learning the conformal properties of how proteins fold, and things that are now commercially deployed, like the Microsoft Azure Personalizer, which any small business can use, and then it automatically learns how to recommend content to maximize user engagement and profits for your website. So these are all very exciting. One thing to note is that they're all in spaces that are, for the most part, completely or mostly digitized. Curiously, when CAS was first opening several years ago, a director of an aerospace company, I won't name which one, although you might be able to guess from the build of this airplane, came to CAST, and he said to me, Yisong, I want to use deep learning to optimize the design, manufacturing, and operations of our aircrafts, but I need some guarantees. And so, but taking that statement sort of at heart and sort of popping up a level, more generally, despite all these successes in deep learning and AI, something is missing. And what's missing are things like interpretability or formal interpretability. If you watched Aaron Ames' presentation earlier today, you'll notice he talking about things like stability and safety. How do you actually get those types of guarantees when you have a learning system? Data efficiency. These learning systems are notoriously data hungry. And if you don't have data, especially if you're working at the frontiers of human knowledge, where you have almost no data collected a priori, how do you actually build these systems in a data efficient way? And finally, the elephant in the room. These systems are massive correlation machines. They learn correlations at internet scale. But there's a huge difference, as we all know, between correlation and causation. And so if we want to use these systems that can make interventions in safety critical settings and high stakes scenarios, understanding how to disentangle correlation versus causation are very important. Now, how do scientists and engineers figure this stuff out? Well, we build symbolic scientific knowledge. And one could think of scientific knowledge as basically code or symbolic. And this, I'm just using E equals MC squared as just a poster child example. But you can go much further beyond this. And so in the spectrum of symbolic knowledge that we can think of blending with AI systems, one can think of things that are much more precise and things that are more qualitative. On the super precise side, you have things like the governing equations of some system, like E equals MC squared. Slightly further is things that are not fully characterized governing equations of a system, but partial characterizations, such as I don't care about characterizing the full properties of the system, but I care about whether or not the system blended with learning has properties like stability, which is a projection or a partial characterization. On the more qualitative side, you have things like behavior. So I have a collaboration with Epic Games on AI for Fortnite. And there, the game designers want to encode high-level domain knowledge, like when to be aggressive, when to be passive, when to hide, when to attack, and have that be encoded in some vocabulary blended with learning. And of course, on the super qualitative side, you have things like comfort, where the expert is a subject that's trying to tell you how well they like or dislike a system. And the conceit of neurosymbolic modeling is that we want to build unified frameworks that inherit the best of both worlds. The rich flexibility and contextual reasoning power of learning blended with the interpretability to formal guarantees and potentially the ability to tease apart correlation and causation with these symbolic inferences. And so on the one hand, you have symbolic models that are interpretable, verifiable, easy for domain experts to encode their domain knowledge, and of course very data efficient. On the other hand, you have neural networks, with scalable algorithms, hyper-flexible, can handle very messy data, and is easy to get started with all the wonderful software packages that we have developed today. And neurosymbolic modeling is really about bridging these two, providing this bridge. And we have some early successes in this, a lot of this sponsored by CAST. So this is an example called Neural Swarm, where a fleet of drones, here it's 16 in total, commercial drones, are flying in tight formation close to each other in a way that it's very difficult or impossible to achieve using standard controllers that's given to you off the shelf. And the reason why they were able to achieve this in such a cost-effective way is because they learned everything that was hard to model using symbolic equations. And the symbolic equations, of course, govern all the natural default behaviors of the drone. And so just to give you a sample, a taste of what this looks like, you have what's basically a standard ODE defining a control system defining a quadrotor. The green part's symbolic. If you're not an expert in drones, don't worry. It's just meant to tell you that that's the part that's provided by the domain expert. And then there's a part that's learned. And the part that's learning is learning things like the interactions between drones when there's downwash from the higher drone pushing air on the lower drone, which could potentially destabilize the drone. And what the big takeaway message is that if you blend these systems in a synergistic and harmonious way, you get both the flexibility of learning and you preserve all the control theoretic guarantees that you care about. Okay, and so we've done this in many projects. We've studied boundary conditions, dynamic environments, sharp nonlinearities, contact dynamics, and of course multi-agent interactions, all using the same high-level philosophy, of course, instantiated differently depending on the needs of different projects. One thing to note is that these systems that you see in front of you, they all use a quote-unquote fixed neurosymbolic architecture, a fixed way of blending neural networks with symbolic knowledge. And one of the long-term goals that I have that I'm really excited about pursuing is how do we automatically find the best architectures needed to fit the application need so that you get scalable, interpretable, composable, verifiable, flexible systems. A related direction is using these types of neurosymbolic models to better understand the world. So rather than AI for autonomy, AI for scientific understanding. And just to ground this in a concrete example, consider the application in behavior modeling. We have a lot of behavior neuroscientists here at Caltech who study the behavior of animals as you manipulate their brain activities. There are other behavior analysis projects that are of interest as well. The problem, of course, is that sharing data is very difficult. Sharing insights is very difficult. Every setting is different. Every experimental setup is different. And you end up getting sort of a bespoke solution for every application. But of course, all of these scientists have common domain knowledge. They have a vocabulary, for example, in this case, of behaviors, an entire taxonomy that has been sort of refined over decades of collective science. How do we encode stuff like this directly into the AI system so that it can learn as quickly as possible with minimal training? And so the first step to doing this is, of course, you have to learn a symbolic representation. What do I mean by that? So here is an application where we did automatic key point extraction, where from purely looking at video, we can extract relevant key points and poses from the animals. Historically, this was done with annotations. You get a biology PhD student who did not sign up to be a PhD student to do this. Annotate, frame by frame. Where's the shoulder? Where's the tail? Where's the head? Over hours and hours in order to train a machine learning algorithm to do this automatically. And every time you have a new laboratory setup, new lighting conditions, new this, new that, new animals, you have to do this process all over again. And so what we did was developed a single algorithm that is able to extract symbolic representations, such as key points, for novel viewpoints, novel organisms. So what you see in there on the bottom, on the left bottom row is a jellyfish. Impossible to track with key points using classic approaches. Yet we were able to do this out of the box. So taking a step back, I want to be motivated by big science questions. And this is one that, of course, has been in the air at JPL and NASA for a while, and it's one that I continue to be motivated by. Imagine that you want to explore the subsurface oceans of Europa, which is a moon of Jupiter. The reason for that being it's one of the best places to look for life outside of Mars and Earth within our solar system. What you need is a robot with limited connectivity to satellites on the surface that figures out how slippery things are, how much traction there is, goes into the underwater lake, swims around, which requires neurosymbolic autonomy programming, understanding the structure of the decision-making needed to make fast and safe decisions on the fly. And then once you're there, you need to be able to reason about whether or not what you're measuring is actually evidence for signs of life. And that requires neurosymbolic knowledge programming for behavior and scientific analysis. And so this is really the big vision that I have, that I want to pursue in the next several years. I've shown you a few examples of results that are taking baby steps towards this direction, and I would love to do more, and happy to discuss, and they'll be at the reception tonight. Thank you. With that, I'd like to invite the next speaker, Ray.
Hi, everyone. My name is Ray. I'm a fourth-year graduate student at CMS, working with Professor Katie Bauman. And today, I will introduce to you another autonomous system where learning has shown great promise in the performance, which is the magnetic resonance imaging, or MRI. As you all probably know, MRI is an indispensable technology for clinical diagnosis and biomedical research. It has a wide range of applications, from pathology detection to tissue segmentation, functional imaging, or spectroscopy. Very important in a lot of aspects of clinical practice and research. Despite its numerous advantages like great soft tissue contrast, a significant disadvantage of MRI is that it has a slow acquisition process. This leads to lower throughput at a hospital, for example, and higher scan cost. This also leads to patient discomfort and potential motion artifacts. So compared to another very popular technology, computed tomography, or CT, an MRI scan could last 3 to 4 times longer, ranging from 40 to an hour. And the patient needs to stay still in the machine for the entire duration of the scan. And when they get nervous or get uncomfortable, they tend to move. And if that happens, you will see images like on the right, where the artifact due to the motion kind of covers the important feature in the image. And this might lead to a rescan, which takes extra time and cost. So there has been a strong interest to accelerate MRI scans, and a very popular way to do it is the compressed sensing MRI, which solves an imaging inverse problem that I will introduce to you now. So in this setup, you have some ground truth image that you're trying to reconstruct, and normally in MRI, you take all the Fourier coefficients of this underlying image using your MRI machine. And in compressed sensing MRI, instead of taking all the measurement, you only take a subset of them, let's say the red region. And if you take a naive inverse Fourier transform, you will get a low resolution image that don't have a lot of details, and you rely on some algorithm to give you a high resolution reconstruction. So in this case, where you have to kind of trade off between different measurements for the best performance, there are 2 important questions we need to consider. The first one is which set of measurements should we take? Like how to get most information out of the MRI machine so that we can best do the downstream processing. And the second thing is how to make the best use of these measurements. And there are a big line of literature that investigate both of these questions. And most of the prior work actually focus on getting this image reconstruction. The metric they use is to have the closest reconstruction as possible to the underlying ground truth image. So they have some training procedure where they minimize some image similarity loss between this reconstruction and the ground truth. So in our project, we're kind of taking a step back and rethink, what is the goal of doing MRI scan in the first place? Do we get the image just to get an image? Probably not, right? We are interested in some downstream task after we get these reconstructions. So if we take a step back and look at these applications in MRI, we will find out that in most of these applications, there are certain regions that we care much more about than what's outside. For pathology detection, we're interested in where that pathology shows up and what's the condition of that pathology lesion. So there's often some region of interest that we care a lot about. So we are motivated to ask this question, could we improve the MRI system such that the accuracy of a specific region of interest, or ROI, or some downstream task is optimized? And the quick answer is yes, we can do that. So how do we do it? We're using a recent deep learning technique called co-design, which jointly optimizes the entire MRI system end-to-end from sampling to reconstruction to downstream processing. So In most existing work, like I said, people focus on getting this reconstruction image, but in our case, we instead focus on some specific downstream task. Like in this case is the reconstruction of a ROI that contains a certain pathology. And we also investigated this for some other type of task like tissue segmentation or pathology classification. So this, at the first glance, seemed very easy to do. You could just change your loss function, change the final prediction module, but it's actually more complicated than that. So here's a comparison between our approach and this traditional approach to CSMRI, which separately deal with reconstruction and task prediction. So in this case, you have some predetermined sampling pattern that's fixed, and then you train some neural network to generate image from these measurements. And after you get the reconstruction, you apply some existing algorithm or another reconstruction that you train separately to do the processing. A naive attempt to what we want to achieve will be using some task-specific loss function to train these three components in an end-to-end fashion. But if you look at this example on the slide, like this actually achieves like a worse performance than if you deal them separately. Because this task like prediction information is very high level, it's very hard to back propagate that information all the way to sampling and reconstruction. So this naive approach actually doesn't work very robustly. In our case, we propose something different. Instead of directly optimizing for the task-specific loss, we will first tune our system to pre-train for a reconstruction loss so that it can effectively extract information from the measurements. And then we will use a task-specific loss function to do the fine-tuning. So this is like a two-step process. And this is known to be effective in training a lot of the modern deep learning models. And as you can see from this example, there's a significant increase in performance from around 80% in terms of DICE score for segmentation to more than 85%. So we have a lot of simulation results, but I think it will be more exciting to show you some of our like real implementation on like a Siemens scanner. So on this slide, like nothing is in simulation. We have actually coded a sequence that we learned with machine learning on a real scanner. So just to give you an idea, like this on the first image, this is the Foley sampling scan, which takes 330 seconds to acquire, and basically the highest quality that you can get using this sequence. And this is the traditional compressed sensing MRI sequence, which accelerates the scan by 4 times, but you can see these like blocky artifacts like in the image, and you can't really see the detail of the menisci very clearly. So this is the traditional approach, and obviously we want to do better than this. So in our case, we have our 4 times accelerated sequence implemented, so this only takes 82 seconds as well. And if you compare like our reconstruction to the traditional approach, there's a significant increase in like PSNR or reconstruction quality in the target region. And this is also the region that we optimize our sequence on, the middle of the knee around the meniscus. And it roughly has the same level of visual quality as the Foley sampling scan. So I think there's a great potential in our approach to accelerate the current MRI pipeline by maybe a factor of 4 time reduction. Yeah, so some quick summary. Hope that I can convince you that machine learning improves MRI system via end-to-end co-design, not just for reconstruction, but also for some downstream tasks that we ultimately care about. And our sequence has been implemented on a real Siemens 3 Tesla scanner, achieved 4 times acceleration as we desired, and maintained almost the same level of visual quality in the target region compared to a Foley sampling scan. There are a lot of future directions that we're trying to push on, and one of them is to leverage the idea of active sensing. So in the current setup, we're more like learning a closed, like an open loop control where we learn it offline and directly apply this like strategy to any patient that might come into the scanner. I think it will be interesting to learn a sequential sampling strategy using like kind of feedback loop control to do the optimization for our downstream task and reducing the uncertainty in the prediction. Yeah, finally, I would like to thank our collaborators and advisors. Without them, this project would not have been possible. And thank you very much for listening.
Thanks. The next speaker is Roni Goldshmid.
Hi, everybody. My name is Roni, and I'm a postdoc in John DeBerry's lab. And today I'm going to be talking to you about visual anemometry. Visual anemometry is a set of measurement techniques. It's a class of them that uses visual observations of fluid structure interactions to predict the flow conditions. And what I mean by that is an example that I'm going to demonstrate today is I'm going to show you how we can use a video of using a single camera that looks at how vegetation moves in the wind to predict the wind speeds. And my favorite example as to where this could be a useful application is wildland firefighting. Firefighters today need information about the wind to know where and how fast the fires would spread. And today, they take a piece of cloth to determine the direction of the wind, take a handheld anemometer, orient it into the direction of the cloth, and then have a single point measurement at chest height to predict where the fire is going to spread out. And my method, or our method, will actually allow them to take a drone, fly it up, look down, and get a full map with a single vector at each piece of vegetation. And to do this, I went into cast for many days and many hours of long, loud fans, but I collected data with an overhead camera that I installed 5.5 meters from the ground. I installed a 2D sonic anemometer to provide ground truth measurement, and brought in 8 species of vegetation, ranging from 1 meter tall grasses to 4 meter tall trees. And as a qualitative, As a qualitative first overview, here we're looking at an overhead view of an oak tree, which is a stiffer of the 2 examples that I'm going to show you. And on the left column, I swear it's not a still image. These are videos of 1 and 2 meters per second that the trees were exposed to. And as you can tell, in this range, it's very hard to tell the difference between the 2, and it's hard to even tell that there is wind blowing in the background. Whereas in the intermediate range, that middle column, we can very well tell the difference between 4 and 6 meters per second, and we can visually tell that one is exposed to higher speed than the other. And when we compare that to a much more flexible tree, a camphor species, we can again see the difference between 4 and 6 meters per second in the middle, that it's easy to distinguish between them. But then when we move to the high range, we see a limitation again, because the tree has deflected maximally, it's moving at its maximum frequency, and it's hard to tell the difference again. And so in order to quantify the kinematics of the trees, I selected a region of interest. I computed cross correlations and spatially averaged it to get a single vector per tree. And I wanted to model it using a sigmoid logistic curve. And the reason behind that is because we saw that at the low and high wind speeds, there was no real correlation between the wind and vegetation kinematics, but then there was this middle range that did have that correlation. And so if we start looking at some of the raw data, we can see that here's an example of the grass. This is a camphor tree, so one of the flexible trees. This is a mesquite tree, which is a little bit more stiff. And here we have another stiff tree, more flexible, another relatively flexible, and another one, and something in the middle. And it kind of looks like a big blob of cloud, and it doesn't really look like it's following that original model. But when we use curve fitting using 3 degrees of freedom, we can see that the data is going to collapse really well. And so now I can say that with a single camera and a single anemometer, I can get a full map of the wind with a single vector per piece of vegetation. And in the future, I'd like to explore whether these degrees of freedom actually provide more significant information about the structural properties of the tree that I'm looking at. And let me know if you have questions later. Thank you.
All right, so we're going to have a slight change of schedule. The next speaker will be Ryan Cosner.
Hi, everyone. So I'm going to be talking about safety for uncertain robotic systems. And just to motivate it, I want to talk a little bit about like the cast moonshots. And so we obviously want our robotic systems to be safe, but specifically for the cast moonshots, we have things like our satellites, and they're going to be operating really far away from us. We're not going to be able to do maintenance. If something goes wrong, it's a really big deal. So we want those to be safe, of course. Our robot partners, when we're interacting with robots, it's obviously really important that they don't damage the humans that they're trying to assist. And then, of course, for transportation, we don't want our robots crashing. That's a really important component of transporting people. And so the tool that my lab uses is control barrier functions. These make the assumption that you have some understanding of your system dynamics. And these are all different systems that we've applied this method to. So this is a very general understanding of the dynamics model. And we formalize safety as the zero super level set of some function h. So we just have some function that describes what safety is for our particular system. And then there's a mathematical theorem that says that if this inequality is satisfied, which you can make sure it's satisfied using your controller, then you achieve safety for the system. And that's great, but for real world systems, we don't actually have the true dynamics. So now we have some uncertainty. There's all of these hats everywhere because we don't know what the truth is. And so we might have model error. And this could be like a drone delivering a package, and we don't know what's inside of the package. So all of a sudden, our understanding of the dynamics could be very wrong from what it actually is. Or if our system is a bunch of vehicles operating together, we might not know what the other vehicles are going to do. And so there's uncertainty in their actions and their dynamics. We can also have measurement error, where we might have the segue here, and it's actually at the full image, but we think it's at the blue images. And that can lead to a lot of error in trying to keep this system safe. Or we might have measurements here. We've got a depth reading on the right side and the video feed on the left, and it's clearly there's a lot of errors that are appearing on the right-hand video. And so one method for dealing with this is looking at bounded uncertainty. So you can take your model error and your measurement error and just say there is some maximum possible that I can see in either one of those. And if you do that, you can augment the theorem that I brought up earlier and add these additional A/B terms here and just say we're going to make sure that we're robust to the worst possible thing that can happen at every moment. And that works. We've done it. So this is the segue not hitting the blocks. But it's not particularly exciting, right? We've said the worst possible thing that could happen is happening all the time, and we're going to make sure that doesn't mess us up. And then we ran it on this quadruped, and it's trying to get from where it is to the other side. And like the last speaker, this is not a still image. This is a video. And the quadruped is trying to walk across, but it's so conservative because of these bounded errors that it's not able to move at all. The safest thing in driving your car is to just leave it in the garage. And so what we've done since then is, okay, well, we have these guarantees of safety, but we still want the performance. And so one of the methods that we looked at, and this is done a lot in our lab, is preference-based learning, where we look at for this case, we're looking at a preferred risk level. And if I have an operator that wants to drive that quadruped across the room, they might not be able to tell me exactly what their performance and risk cost function is. And so we're trying to learn that and figure out what's optimal for them. And so here's where we started. And then through multiple runs of adjusting these A/B functions, we're able to get the quadruped to walk through much more challenging terrains and achieve its performance goal of getting from one side to the other without colliding into the obstacles. And then that's great, but what's a little tricky about that is we lost our guarantees. We said, oh, this was really cool. We got beyond our bounded uncertainty problems, and we achieved performance, but now we've lost the guarantees of that theorem that we had. And so I wanted to look at using learning in different ways while still achieving both the performance and the guarantees. And so in this case, we're trying to fit an error to the dynamics residual. We have our robot Amber here, who is trying to walk across these yellow stones, and there's a lot of uncertainty in our robot and like its joints and how it moves. And so what we've done is we've learned a dynamics residual to account for the uncertainty that we have in the system instead of just bounding it. And so it's able to walk across and place its feet where it needs to place them. All right. And then we wanted to then say, oh, well, what if the uncertainty isn't just a deterministic signal? It could be a distribution, and we want to remain robust to that as well, while also achieving performance. And so in this one, there's that image that I was showing, the video I was showing earlier of the uncertainty and the depth, and it's able to adjust its understanding of that uncertainty as it's moving forward so it can get close to the obstacles without colliding with them. And then our last thing here, and this is what you saw earlier in the cast arena, is our drone, and it has learned an uncertainty associated with the dynamics of the ball and how it affects the drone. So in conclusion, control barrier functions are a useful tool for guaranteeing robotic safety, and we can create safe, performant, real-world robots by learning the errors in the system. And thank you to all of my collaborators. This has been very fun work, and thank you all for listening.
Okay, so the next speaker is Berthy Feng.
Hi, my name's Berthy Feng. I'm a fifth-year PhD student in Professor Bauman's lab, and we've been working on developing data-driven priors for scientific imaging. A lot of scientific disciplines have objects of interest that cannot be observed directly. But I work in computational imaging, and our goal is to be able to produce photos of things that we can't see with our own eyes. For example, a black hole, in the case of astronomy. So the way we do this is by first considering measurements taken by physical sensors, for example, radio telescopes. And then from these measurements, we try to infer the original image that led to the measurements. However, the measurements are quite sparse and they're corrupted. And so they're actually not sufficient to get the original image. Here's what would happen if we were to naively invert the measurements into an image. Not very interpretable. But if we wanted to get a more human interpretable image, we could impose a prior on the image reconstruction. In 2019, we got the first image of a black hole, which was the result of handcrafted priors known as regularizers. These regularizers imposed basic image assumptions like spatial smoothness and compactness. But we could also go further in the prior and say, well, we know that this is an image of a black hole, and so we fit the image according to a ring model of black hole structure. So we see that different image reconstruction approaches tend to lie somewhere on this spectrum of varying strength in the prior. On the left-hand side, we have traditional imaging, where we use regularizers to impose very basic image assumptions and try to let the measurements speak for themselves. On the right-hand side, we have model fitting, where we constrain the image according to an underlying physical or geometric model. But both of these extremes are limiting in some sense. On the left-hand side, pure imaging will limit the diversity and the richness of the possible images. On the right-hand side, model fitting will limit the potential of discovery and also is prone to overfitting to an incorrect model. We've been working on score-based priors, which are a type of data-driven prior that would allow us to fill in more of this spectrum. So with our approach, we can flexibly design different priors by collecting different data sets of training images for the score-based prior. So for example, we could collect a data set of images that contain generic objects, thus targeting generic natural image statistics, train the score-based prior on these images, and then use the prior in the imaging process. This is a different interpretation of the original M87 image. We could target different image statistics and biases by changing the training data for the prior. For example, training on a data set of black hole fluid simulations. And that would get us a different image reconstruction. We could also train on a simplified geometric model of black holes, which would lead to another image. So these different image reconstructions, they all agree with the observed data that was originally taken by the EHT telescopes. The only difference is in the assumed biases of the prior. And using this approach, we can assess all the different images under different imaging assumptions and find out which features are dependent on the prior and which are prior invariant. For example, the ring-like structure or the brightness asymmetry of the ring. So to summarize our work, score-based priors are useful for a variety of imaging problems. I've talked about astronomical black hole imaging today, but we've also been able to demonstrate this on medical imaging tasks and photo enhancement tasks. Score-based priors are quite expressive because they're rooted in deep learning. So unlike traditional regularizers and data-driven priors, they're able to model more complicated image statistics. And I didn't touch on this today, but we are also able to provide uncertainty quantification. whereas other deep learning-based approaches to solving imaging problems don't necessarily give you accurate uncertainty. So yeah, overall, we're quite excited about this direction of score-based priors and believe that it's a good way of incorporating deep learning into the imaging process in a principled way. Thanks.
All right, last but not least, we're going to cap off this session with the one and only Michelle Effros.
All right, so thank you so much for the invitation. It's a pleasure to have the opportunity to tell you about some work that we've been doing in my lab and in some cases in joint work with Richard Murray's lab. I think that this invitation came about because of some work that we did specifically under CAST, which was joint work between the two of our groups. And the question that we were interested in was a question about distributed agents and their collection of information. So imagine that you have a collection of devices, they're flying around and they're gathering information. They're working together in the sense that each one is playing a role in some task where you're trying to understand the environment that everybody's traveling in, but they're independent agents flying autonomously. And we're going to allow communication between these devices and some sort of central processor. But for simplicity, we won't have communication between the devices themselves. And our goal is to be able to do whatever operations these devices are working on in this shared environment. The typical approach that people take in designing systems like this often looks like this one. So we have communication resources in both directions. They may not be equally expensive. Often the autonomous devices are wireless, they're battery powered, and so communications is expensive. The central processor may have unlimited power. Communications from the central processor may be a lot less expensive. But nonetheless, often the communication is done in such a way that the primary flow of information is going into the central processor, where that information is then processed, and maybe occasionally a little bit of information goes the other direction. Maybe, you know, hey, you might want to look over here. I'm not sure what's happening there. Can you collect more information? Sorry. So this is an approach where the primary flow of information is into the central processor, and that's why we have sort of emphasized the in information here. This is a view of the world, which by analogy might look something like this. If you imagine the brain and the little sensors, the neurons at the back of your retina gathering information, you might think of that as one sensor, but really it's many, many sensors that collect data about different things. And you might imagine, I think many people do imagine, that how our brain processes information is something like this. It comes into the retina, it then gets sent back to the visual cortex. The primary visual cortex is somewhere here at the back of your head, and central processing happens there. And maybe a little bit of information flows in the other direction to say, you know, look left, look right. I think there's a predator coming, whatever it may be. But the approach that we take, or took in this study a few years back, was what we called an outformation view of data gathering, because here we want the primary flow of information to flow out from the central processor to the agent. So in the previous picture, you might imagine likewise the central processor sending lots and lots of information out to the sensors rather than the other way around, and maybe a little bit of flow in the other direction. Why might you consider doing this, or why did we consider doing this? You can imagine a variety of advantages, one being that we're replacing the collect and process model of information gathering by instead a predict and then update or correct. So a central processor is trying to predict what all the sensors will see, tell them what they expect to see, and then have the sensors only tell you when they see something different. This will help us avoid a lot of redundancy in our system. It also pushes the processing forward in time, meaning we process first rather than after the data is collected. Imagine the difference between getting to predict what's going to happen and having to study some huge flow of information in the inward direction. It makes anomaly detection really fast. Individual sensors can tell you, hey, that's not what I'm actually seeing, what you predicted. And it allows us to describe the models rather than the data itself, which can be a lot more efficient. Just as an aside, I have a really large interest these days in neuroscience, and this is actually how the brain processes information. It uses this outformation model rather than the information model. In particular, the brain collects this information, it sends it without apparently too much processing to something called the LGN, where a lot of sensory information is gathered. But the primary flow of information is not from the LGN to the visual cortex, but actually the other way around. And the belief is that that has to do with being able to react very quickly to unexpected events, such as these kinds of predator moments, where being able to detect these anomalies is really important to be done quickly. Sorry, I'm out of time, but let me just say one more word. The work going on in my lab involves many different problems around communications and data gathering, as well as some work in neuroscience, and I'm happy to talk if people want to talk about any of those topics afterwards. So thank you.